Lecture 7-3, Measuring and Predicting Earthquakes. When we talk about earthquakes, typically we're going to talk about a scale that we use to measure them. The first scale that was widely used was the Richter Scale. It used the amount of damage at a given place using observations by eyewitnesses. There are 12 steps in the scale, each having its own description, so you know which one to assign. It's not that accurate of a scale to compare one earthquake to another, because when earthquakes occur in different locations, you have different soil structure, you have different types of buildings being built. An earthquake in downtown Japan will probably not do as much damage as an earthquake in downtown Nashville, because the buildings in Japan are designed to withstand an earthquake where the ones in Nashville are not. You see that the scale here goes from 1 to 12, 1 at the top, where you don't feel anything, 12, damage is total, waves seen on the ground, where you see the ground actually fluctuate up and down, and objects thrown into the air. We still use the Richter scale today, but as extra information. We look at people's observations and we can create maps saying, well, in this area they really saw a lot of 11s, this area they only saw a lot of 6s. You can see then kind of the progression from a small earthquake to a large earthquake, and of course, the closer you are to where the earthquake occurs, the more damage you're typically going to see. So this can actually help us pinpoint an area where the epicenter is without having to look at a seismograph reading. Looking through the scale, you can see that this is pretty much easy to give a number to, but again, it changes so much from place to place because you have so many other variables, building structure and soil structure being the main two. The Richter scale came about with the use of a seismograph. It measures the amplitude of the seismic waves. That's how much they move, kind of how much they move up and down, and is related to the amount of energy released. Again, we use a seismograph for this, and we get a nice little reading. We can use that reading to tell how big of an earthquake it was. An increase from 6.2 to 7.2 on the scale indicates about 10 times more ground motion, about 32 times more energy released. So it's what we call a logarithmic scale, which means that a linear scale, you see a nice little line here. Logarithmic, that means that as we go up, or in the Richter scale from like a 1 to a 4, we see a curve up. We see a lot greater change the higher you go up. It does provide accurate measurements of nearby and small quakes, but for distant earthquakes and large, very large earthquakes, we kind of had to go to a different scale. This is a seismometer. The graph it produces is what we call a seismograph. Now, all seismometers pretty much work the same way. We have some way to record. On this one, you can see it's a piece of paper. There's ink inside of the little arm here. And the difference is that you have part of this is attached to the surface. So you can see that this whole thing is attached to the table there. This part here, where the little arm comes out to dispel the ink to see the motion, this is free from the ground, which means that either of these can be suspended or at least designed in a way that the whole seismometer itself can shake side to side when the vibrations come, but this will stay stationary. So this goes back and forth, but this stays the same. And that's the reason why we can see the little lines here. Of course, the bigger the lines, the more motion there is. Now, this is our seismometer, which is the EQ1 seismograph. It is down in the first floor in the side room. And the way this works is pretty simple. In here is the coil of wires. And this is a magnet. And as the vibrations come through, the magnet will move up and down, and which causes a change in current, a change in charge of electrons. And they flow through to this little device which connects to a computer, and that reads it. Inside of this pan is some oil in here that keeps it from moving too much. It slows down its motion. And the computer actually only looks for certain types of vibrations. It's not designed really to pick up everybody walking in the room. If you walk right next to it right now, it will pick that up, but it needs to be fine-tuned. But it can record earthquakes pretty much from anywhere in the world, except in some locations, if they're powerful enough. We can detect small earthquakes nearby, but we need a very large earthquake to detect it from very far away. This is one of the readings that we took with ours. You can see this is what it looks like normally, and then here's where you can see the vibrations start. And you see that they move down. This actually is enough information for us to figure out how far away the earthquake was and start to get an idea for how powerful it was. Now, the modern scale used today, especially for large earthquakes, are the moment magnitude scale. It's calculated by multiplying the area and the amount of displacement or amount of movement in the slip. So how much actual movement was there? So we need more information than just a seismograph. It is more reliable for earthquakes that measure above magnitude 7 on other scales because they only refer to part of the seismic waves. We're referring to all of it. It uses information gained from seismographs in multiple locations. Our seismograph is connected to the internet. We can upload our information, and other scientists all across the world can use our information anytime there's a major earthquake. And by collecting all this information, you get a better understanding of what happened in that earthquake. Now, with the reading of it, we can actually, first thing we do with the seismograph readings, we can tell how far away it was. We can locate the epicenter. Now, we need information from at least 3 different seismometers to figure out where an earthquake actually happened. We call this triangulation. It's the same thing as the GPS on your cell phone. Your cell phone can connect to different GPS satellites in space, and it needs to connect to at least 3 of them to figure out where you are. If you just connect to one, it can tell you it's somewhere this distance away, but it gives you almost infinite number of locations. If you have 3, they pinpoint to one specific spot. And of course, the more satellites you connect to, the more exact your location will be. Now, the difference between the arrival time of the P and the S waves tells you how far away. We know the P wave comes around 7 kilometers per second, and the S wave is about 3.5. Well, if I know the difference between how fast they're moving, and I get, say, they happen 10 minutes apart, I can tell how far away they started. It's kind of like the basic math problem. You have car A going 60 miles per hour, car B going 50 miles per hour. We know after an hour they're going to be 10 miles apart. So we use that kind of working backwards to figure out where the earthquake happened. So when the first little vibration happens, we know that's our P wave because the primary wave is the first wave. Then we look for the second wave to show up, and it's going to be bigger. The S wave is almost always going to be bigger than the P wave. And then, of course, we're going to see the surface waves are going to be not far behind that. So the body waves, the P waves, the S waves, those are the first thing we need to know. We need to know how long does it take between those 2 waves. That tells us how far away the earthquake was. And so same thing here. P wave is that first vibration. S wave is when we see the next large section. The difference in their time will tell us how far away it is. And if I also know the size of my vibrations and I know how far away it is, I can tell you the size of my earthquake or the magnitude. The amplitude here, that goes to how much does it shake? How much vibration is there? So difference in time tells us distance. If I use that with how much shaking there was, I can figure out how big of an earthquake we have. And this is just a little diagram showing you triangulation. Let's say as a seismograph in Minneapolis that says it's so many miles away. Let's say it says it's 500 miles away. Well, it doesn't tell me direction. It just tells me distance. And so I could draw a circle around Minneapolis that's 500 miles wide. Now I know that earthquake happened somewhere on that circle. If I go to another reading from Charleston, let's say it says 400 miles away. I draw another circle with the radius of 400 miles. Now, wherever those 2 lines cross is where my earthquake happened. But if I only have 2 lines, you see they either can cross there or there. It takes a third reading, let's say this one in Detroit, to figure out exactly where did the earthquake happen. And the more information we have, the more precise we can be. Now, predicting earthquakes is difficult. They are considered almost part of like meteorology in a sense, just because their predictions have percentages attached to them. We can always predict where earthquakes will happen because earthquakes typically don't happen outside their usual locations. They're going to happen mostly at plate boundaries. But then I also know southeastern Missouri gets tons of earthquakes each week. Yellowstone National Park gets a huge number of earthquakes every week. But predicting when is very, very difficult. Foreshocks, those are little vibrations before an earthquake. And they don't always happen, but they do happen a good number of times that if we detect some small vibrations, we kind of prepare for a bigger vibration. The ground surface can also tilt up because of the stress being acted on it, which also can change water level in, like, say, wells or something like that. And we actually have something called a tilt meter. And it measures how much the ground tilts so we can tell if its stress is building up, if that needs to be released in the form of earthquake. Past history, we look at like how often do major earthquakes happen. That doesn't tell us which day it's going to happen, but they can tell us, I would say, within the next 20 years, we know we're going to get a very large earthquake. And oftentimes, nearby earthquakes can trigger other earthquakes, and so we look for that information, something along the same fault line or something where we know it could weaken our area that could cause another earthquake to happen. Predicting earthquakes is very difficult right now, but we study them as much as we can. The more information we have, we may someday be better able to predict them. At least we should be able to build buildings that can withstand earthquakes more easily.